Welcome to Brain Vision.
So benzoic acid is HC7H5O2. It is a weak acid, so it does not completely dissociate, but an H plus comes off, plus the C7H5O2 minus. Now, you might also see this written as the benzoic acid plus water, because acid-base reactions are done in water. And then the H2O and the H plus come together and form H3O plus C7H5O2 minus. Now we can look up the value of the equilibrium constant for the acid. It is 6.3 times 10 to the minus 5. So having this reaction, knowing that the acid is aqueous, water is a liquid, the hydronium ion is aqueous, and the benzoate ion is aqueous, we can set up an ice table to figure out the concentration of H plus. Now, since water is a liquid, it is not going to participate in the equilibrium. Now we have a 0.1 molar solution of the acid, which means we start out with none of our products. And if we start out with none of our products, the reaction has to shift to the right to make some product. How much? The thing is, we don't know. And if we don't know, we call it X. But we're making it, so it's positive. We do know that there's a 1-to-1 ratio between the H3O plus and the benzoate ion, because our coefficients here are 1. So the amount of H3O plus I make is the same amount as the benzoate ion that I make. If we come over to the other side, if I made the stuff on the right, I must have used the stuff on the left. So that's going to be negative. How much? I don't know. But I know for every one H3O plus I made, I used a benzoic acid, so it's minus X. So at equilibrium, we started with 0.1. It went down by X. For H3O plus, we started with none. It went up by X. And for the benzoate ion, we started with none. It went up by X. And we can use this ice table, and especially the E, or the equilibrium line, because we can set that equal to our Ka, because we can look at our law of mass action. So if you come up with the law of mass action expression, the equilibrium expression, you put the products in the numerator, raised to the power of their coefficient, these are both 1, divided by the reactants. But we don't include water because we don't include pure solids or pure liquids in the expression. Now, how did we represent each of the things in the numerator? X and X. So X times X is X squared. And then we have 0.1 minus X as our denominator. Now we know that's equal to 6.3 times 10 to the minus 5. Now you may have learned a little trick. Since K is small, we can assume that we're not going to make a lot of our products, because this is a very heavily reactant-favored reaction. K is much smaller than 1. And so what that means is that this minus X is actually going to be a small number. And so we assume that that is going to be essentially 0. And so by doing that, we make our math easier. We don't need the quadratic equation. And so we just say it's equal to X squared over 0.1 is our 6.3 times 10 to the minus 5. So now we would do the math. And essentially this is like saying it's over 1, right? So we have 1 times X squared, or X squared, equals 6.3 times 10 to the minus 5 times 0.1, which is 6.3 times 10 to the minus 6. And then you've got to square root both sides, and you come up with your answer of X as 2.5 times 10 to the minus 3 to our two significant figures. And so what does x represent? We've done the algebra. What's the chemistry? Well, let's look. X is the amount of H3O plus. So if we make this molarity, that is the concentration of the H3O plus. Now we also need the pH. So remember the equation for pH. pH is equal to the negative log base 10 of the concentration of H3O plus. So we just have to take the negative log of 2.5 times 10 to the minus 3. And so when we put that into our calculator, we get 2.60 as our pH. Now just remember rules of significant figures and pH. This, it looks like, has 3 significant figures, but in pH calculations, only the numbers after the decimal point are significant. So since there's 2 numbers after the decimal place, this actually only has 2 significant figures. So one weird part about significant figures and decimal places when we deal with pH.